Okay, it's time to go ahead with the program of the Smart Grid workshop. The next speaker has been very smoothly integrated into the program. However, we have to say a few words that it's a special speaker today. He is a speaker of Halmstad Colloquium series. Halmstad Colloquium is a project led by two research centers here in Halmstad University, Center for Research on Embedded Systems and Center for Applied Intelligent Systems Research, and it is supported by the Swedish Knowledge Foundation. It's my special pleasure to introduce now our distinguished speaker for today. He's Professor Kishor Trivedi. He's a Hudson chaired professor in electronics and computer engineering in Duke University, North Carolina, US. Kishor Trivedi has been with the university faculty at Duke since 1945, and one of the major areas was reliability, performance, and assessment of different systems and applications. He has published more than 480 research papers. He has supervised, he will fix me if I'm wrong, 43 PhD students so far. Apart from that, he has been heavily involved into the teaching, and he has co-authored a few books. One is quite famous. It is dedicated to the stochastic processes, Markov processes, and queuing systems. It has several editions. The second edition, the last one up to date, has been published in 2001. Also, it's important to mention that Professor Trivedi has been involved, together with his team, into the design of simulation tools, simulation packages, which have been used widely through over the world in more than 500 research environments, including the industrial ones, and noticeably with some giants in industry like Boeing or Cisco. Professor Trivedi is a fellow of IEEE. He is the Golden Core member of IEEE Communication Society, and let us welcome him today and listen to his presentation.
Thank you, Alexei, for inviting me and Halmstad University. Only thing I have a complaint, he made me about 30 years older today. I joined in 1975. And you said 1945. That would have been before my birth. Would have been something interesting. And also, I did not, when he invited me for colloquium, I offered 4 or 5 different topics as I usually do, and he picked this topic, and I was very happy with that. Then I realized that this is embedded in a smart grid workshop. Now, fortunately, I've done a little bit of work on smart grid, so I have tried very hard last few days integrating that piece of work with the original talk on stochastic petriness that I had. Anyway, so now they also tell me that if you really want to give a good talk, you should have 3 takeaways. That is, if somebody asks you after you get out of the talk, what did you learn? So I just give you the 3 takeaways, and you can read that and get out. I'll be perfectly okay. Right? So the first point is that a mathematical construct known as Markov chains, Markov models, Markov reward models, are useful in quantifying reliability, availability, survivability, performance, ... of many technical systems. How many of you have heard the notion of a Markov chain? quite a few, all right? By the way, Professor Markov was in St. Petersburg, as is our distinguished colleague here, Alexei. And I have personally used Markov chains on real machines at many, many different companies, both computer, communications, and even aerospace. So it is a reality that Markov chains are used very extensively in quantifying systems, certainly at the design time, but also often at the operational time. But what you also find that accurate models, Markov models of real systems, tend to become very large very quickly, so that it is nearly impossible to build such models by hand and solve such models by hand. So model construction and model solution by hand is infeasible for all but simple toy examples. So concise specification, automated generation, and automated solution of such Markov models is possible via the formalism of stochastic Petri nets and corresponding software packages that do exist, including our own, as was mentioned by Alexei. So that's the takeaway, all right? And if you want to hear the rest of the story, fine. If you don't, you learned something anyway, right? I have not been doing this. This is the first time. You are special. First time I have given you 3 takeaways, okay? 3 is also important because my name is Trivedi. 3, right? Whenever somebody asks me a question, I try very hard to give 3 possible answers.
Which one is correct?
So now, connection with the smart grid. The story is that I have been dealing with a topic or term called survivability. You know, whenever there is a new term with respect to quantification of systems, I'm always a little bit suspicious. People generate these new terms either because they don't know the old terms, or they want to write papers, they want to have workshops or conferences and get money from agencies. Because agency will not give money for availability or reliability because they have been around for a long time, but survivability, why not, right? So I went into this term to try and understand whether or not people have created this term just to get more money, right? And indeed, many of the papers, some by well-known people, I found that they were simply using the term to mean what we call availability otherwise, and so on. But I found one definition in an industry standard where there was something new. And I like that. Okay, so I say, okay, this is the definition of survivability, and my task is to now show you how to quantify, how to compute survivability of systems based on this idea. And so I wrote a number of papers, and one of which was with some researchers at Avaya Bell Labs, survivability of pots. You know what pots stand for? Of course, you cook with them, right? Kitchen. No, POT stands for plain old telephone service. People have forgotten what that is, right? So there is a nice paper that we wrote with the Lucent Bell Labs guys, not Avaya, I'm sorry, Lucent. I get mixed up between from AT&T to Lucent to Avaya, etc., etc. And then, without my involvement, a friend of mine who is at Siemens Research Center in New Jersey had started to apply this idea of mine to smart grid environment. And then we got together, and we've been writing some papers on using survivability for smart grid. So let me briefly tell you what it is, and this then is a motivation for the rest of the talk. If you need a motivation. Motivation is that he asked me to talk about stochastic Petri nets. But those of you who are not otherwise interested, I'm giving you some reason to be interested. So survivability, according to this definition that I saw in an industry standard document, is the transient behavior of the system immediately after either an occurrence of a failure, an attack, or a disaster, until system recovers fully to its either the original state or something else. So it's a transient behavior or transient performance of the system conditioned on the occurrence of failure, attack, or disaster. So in the context of smart grid, the performance is taken to be the amount of energy not delivered. Amount of energy not delivered to the customers immediately after the occurrence of failure until the system recovers. And in this sense, it can be seen as a generalization of recovery. Normally, recovery time. Normally, people will worry about when failure occurs, how long does it take to recover? But I'm also concerned with, during that recovery time, how much energy is not delivered. And this then is used in designing, if you will, of the smart grid. So this was the Markov model that was created by my co-authors from Siemens to reflect the recovery behavior after the occurrence of failure in a smart grid environment. Now there is a lot that goes behind it, but I'm just going to give you a very brief idea. So failure has occurred. This is the failure of section I. The grid is divided into many sections. Failure of section I. And that failure may be such that after some quick isolation, you find that the downstream section I+1 has enough active and reactive power. I'm using your terminology, right? Active and reactive power. Or it may be that you find that there is enough active power, but reactive power is not okay. Or you may find even active power is not okay. In any case, after that, there is a demand response kicked in, and based on demand response you find that you may recover active power or you may not recover active power, and then there is an automatic restoration and there is manual repair. So when you start here, and when you come to this state, everything is back to normal, but in the meantime, what have you lost is being captured by survivability. Okay? Everybody okay so far? So this is an example of a Markov model. In particular, it's a continuous time Markov chain, and it is a Markov reward model because different states here have a different rate at which energy is not supplied. So this is a Markov reward model, and I'm not interested in steady state analysis. I'm interested in transient analysis. I want to know what happens when I start here until I get here. So far so good? Any question? Now there is a lot of additional, there is a particular metric called SAIDI that is being used by the power distribution people, and what we are generalizing SAIDI here by means of survivability being one component and the failure frequency being another component, and together we get generalized SAIDI. That's what we are doing here. And so what we have completed so far in a series of papers, I've just listed one paper here. And so the main guy here is Alberto Avritzer, and Sindhu Suresh is a power person at Siemens Research Center in New Jersey, and Alberto Avritzer is my kind of guy, computer guy at that place. And there are many other authors, some in Brazil. Actually, these two are in Brazil. These three are in Brazil. Daniel Menache, Edmundo de Souza e Silva, and so on. And so what has been done so far is, unfortunately, this color, which my student liked, but here it doesn't work very well. Survivability model is used to predict recovery metrics, if you want to call what I just described, of power distribution system. And this is then integrated to get a generalized SAIDI, where original definition of SAIDI is very simple. And then furthermore, by integrating with the power flow equations, this is used to optimize the network. A lot more details in papers that are there. Now what we want to do is to extend this model to multiple concurrent as well as cascading failures. Does that make sense? Mm-hmm. And that will preclude hand construction of the Markov chain and hand solution, which was done so far. So what we want to then do, of course, is use stochastic Petri nets to develop this Markov model for the survivability of smart grid. And then those of you who know a little bit about Markov chains, particularly continuous time Markov chains, should object that how can I assume all distributions are exponential, right? Well, so we want to extend this to non-exponential distributions, and there happen to be non-Markovian stochastic Petri nets. And finally, this is much later goal, that power flow equations are being used together with this Markov modeling, and I want to try and integrate the two together. And in power flow equations, you are dealing with voltages and phases, right? Phase angles, which are continuous quantities. Whereas the Markov chains of the type I showed you are discrete state quantities, discrete state models. So what I want to be able to do is combine continuous state and discrete state systems together into what some people call hybrid models. In our context, we call them fluid stochastic Petri nets. So I want to start with simple stochastic Petri nets, move to non-Markovian Petri nets, and fluid stochastic Petri nets. Now, since you're my friends, I'm not going to tell you about these guys. I'm only going to tell you about that one, okay? Because it's a graduate course, if you will, afterwards, okay? But all this is possible, and it will be done in the context of smart grid. So far, so good?
Yeah.
Okay, so now the outline of the talk. So traditional approach, as I mentioned to you, is that you develop continuous time Markov chain for your problem by hand. And then I'm advocating that may be okay for toy problems, but for real problems you want to use stochastic Petri nets. But before I can tell you about stochastic Petri nets, I need to tell you about Petri nets. And then there are several levels of generalizations of stochastic Petri net, GSPN, and then our version, stochastic reward net. And I will briefly tell you about non-Markovian and fluid stochastic Petri nets. And all this is possible to solve, specify and solve via one of the solution packages that Alexei mentioned, SPNP, stochastic Petri net package. Okay? Any questions, comments? Including what is the meaning of life, why are we here? But I really like the previous, I like a lot of talks here. In the morning, then afternoon, yeah. The previous speaker was really exciting. How do I learn to do that? Yes?
I can ask you something that you couldn't answer when you explain Petri nets, but isn't Petri net also stochastic?
I'm going to tell you about that.
Yeah.
That's the rest of the story, right? So hold on, okay?
Yeah, I wonder what's the difference between the
I will tell you.
Which is stochastic and the thing that you explicitly tell is stochastic.
Yeah, I'll tell you. So in fact, okay, let me tell you. So the Petri net by itself comes from a PhD thesis from 1962 by a person called Carl Adam Petri. I'm not sure whether I'm pronouncing it right. And in which location in Germany? Berlin? He passed away recently, by the way. And his notation did not have any notion of time in it. And the objective was to study sequences, logical properties. And subsequently, stochastics was added to it. And in fact, as far as I know, Carl Adam Petri didn't like that. He thought we are contaminating his notation. Okay? So does that answer your question?
I was thinking of the description I got some number of years ago where you had this firing of the transitions.
Yeah, all that will come.
That was also introduced after the original, you mean?
Yes, original, yes, all that is there in the original notation, but no notion of time. He was only worried about sequences.
Yeah.
Let me give you another connection. You know finite state machines, or state machines, finite state automaton, right? The finite state automatons are also used for logical analysis and sequences. Regular expressions are the sequences that result from finite state machines, right? There is no notion of time there. Once I put a notion of time there, I get a Markov chain, either a discrete time Markov chain or a continuous time Markov chain, depending on how I put time. Likewise, Petri nets are a generalization of finite state machine, but when I put a time there, I get stochastic Petri nets. All right?
Yeah.
But you're not still satisfied. I'm not quite sure why.
I'm not sure if it fits the description I got on Petr Nets when I was reading a book by Petr.
So somebody automatically assumes stochastic Petri nets then.
Yeah.
That's fine.
Written
But this is not what Carl Adam Petri defined. Okay. Okay, so traditionally, suppose you want to study a network router, packets arrive or cells arrive, there's a buffer and they get serviced and so on. Then you study the system for a while, and let's suppose that you abstract the system into, let's say, MD1NQ, whatever that means, okay? So that's the step one all the time. You study the system and then abstract it to some level. And then you say, hey, wait a minute, but I need to generate the state space by approximating the deterministic time into Erlang, M, or whatever, and then you draw the Markov chain by hand. Step two. Step three, okay, now this Markov chain needs to be solved either for its steady state behavior or transient behavior. These are the equations for the steady state behavior, and similarly the equations for the transient behavior. And actually there is the cumulative transient, and there are many other levels of transient. I won't bore you because you're my friends, okay? I won't give you too much details because you're my friends. So step 3a, step 3b, 4a, if possible, after setting up the equations, you solve these equations by hand, if possible, in closed form. And if you cannot do it by hand, sometimes you can do fully symbolic solution from Mathematica, MATLAB, and some of these tools. But many times, even that is not possible. So you write your own program or use somebody else's program to numerically solve these equations, 4b. And finally, step 5 is to calculate the measures of interest, because you're not really, most people are not interested in probabilities of so many states, right? That I really want to know reliability, availability, throughput, and so on, some measure of interest. So among this 5-step process, typically, traditionally, steps 1 through 3, 4a and 5 are commonly handled manually. And so this is a rather tedious and error-prone procedure, especially when the number of states becomes large. So what's the alternative? That's the question, right? Can we find a new approach where you let the computer do all the dirty work, tedious and dirty work? And so one such approach is using stochastic Petri nets. That is not the only one. This morning I met someone who says, I will not be in your talk, which is fine. He uses stochastic process algebras. That's a more recent approach. And so there can be many other approaches. But this is the approach that I like and we've been using. And it was stochastic Petri nets per se were proposed by Natkin and Florin in France and Molloy in UCLA in US in the 1980s. Whereas Petri nets were 1962 construct. And so it can be seen as a modeling formalism for the automated generation and solution of Markov chains, and have been subsequently extended to allow for non-Markovian and jointly discrete and continuous state spaces. So far so good? So first, Petri nets, okay? Not stochastic Petri nets, just Petri nets. So let me go back. I mentioned finite state machine or finite state automaton, right? So a system is quite commonly bunch of subsystems, right? And suppose each subsystem can be modeled by a finite state machine, and these subsystems interact. So overall system is also a finite state machine, but if I want to construct such a finite state machine, it will be a mess, spaghetti. Now some people like spaghetti, I like spaghetti too, but it's very difficult to eat it, right? So the idea that Petri had, Professor Petri had, was that can I come up with a notation where each individual finite state machine can be seen as distinct as possible and yet show all the interactions wherever they occur. So that's the brief idea of a Petri net, that each individual subsystem, sub-Petri net, can be almost seen and interactions are allowed to be shown. That's all. Okay? Formally, we can talk about all the things, but the beauty of this is that various features or behaviors that exist in real systems can be easily incorporated, such as the concurrency, things happen concurrently, or conflict, that two people compete for a resource, two or more people, sequencing, conditional branching, looping, synchronization, sharing of limited resources, mutual exclusion, all these behaviors can be easily incorporated in this notation. And so Petri nets originally, and even today, enable the study of logical properties of the model system. Sequencing, deadlocks, live locks, these kinds of things, okay? So as I mentioned already, Petri net originated from the PhD thesis of Carl Adam Petri in 1962. There are very few PhD theses are remembered for that long. So if you want to write a PhD thesis, write that one, which people will remember. And there are two regular international conferences on Petri nets. ATPN, Application and Theory of Petri Net, still exists, and this is the non-stochastic one, non-timed one. And I was instrumental in starting this series, PNPM, Petri Nets and Performance Models, which was specifically for stochastic and time Petri nets, which has now been integrated or merged with something called QUEST, Quantitative Evaluation of Systems, or something like that. I forget what it is called. So this conference started in 1985. First one was 1985 in Torino, whereas this has been there before. Okay, so original Petri net did not have the notion of time and were used for studying logical properties. But for performance, reliability, availability, quantification, I believe it is necessary to introduce the notion of time and time duration attached with events in the Petri net, as we will see. For this reason, PN were extended to have timing associated with event occurrences, giving rise to stochastic Petri nets. So very quickly, introduce Petri nets to you, and then stochastic Petri nets to you, okay? And if you don't like it, blame it on him because he chose the topic. If you like it, thank me. If you see something good, I have done it. If you see something bad in this, my students, my co-authors have done it, right? So a Petri net is a bipartite directed graph. Everybody knows graph, right, or directed graph. How many of you know of bipartite graph? Very good. And the best way to explain bipartite graph is based on social construct that is no more in vogue, which is that marriage graph. If you have a marriage graph, there'll be two types of nodes, man and women, right? And there will always be a connection between there can only be a connection between a man and a woman, and not between a man and a man and woman and woman. So bipartite directed graph is one graph where there are two types of nodes. In the Petri Net context, one type of node is called a place, and that is normally indicated graphically by a circle. And the other type of node is called a transition, and it is normally indicated either by a bar or a rectangle. And arcs, directed arcs, can be there between a place and a transition, from a place to a transition, or from a transition to a place, but never ever between a place and a transition and a transition. That's the meaning of bipartite directed graph. If you should ever, and most students in the beginning always do, if you should ever have an arc between a place and a place, you will be excommunicated from the Church of Petri Nets. All right? And so formally, Petri Net is a 5-tuple, where P is a set of places, T is a set of transitions, I is a set of input arcs. Arcs are divided into input arcs and output arcs. And M is initial marking, which we will come to in a minute. Okay? So instead of formally defining all this through pictures, picture is worth 1,000 words, right? So in this Petri Net, I have two places drawn shown as two circles, and one transition drawn as the bar. There are two arcs, one of which is an input arc and the other is an output arc for this transition, right? So far so good? And there is a token here. We will come to that in a minute, okay? Tokens are dots or integers associated with places in the Petri Net. A place containing tokens indicates that the corresponding condition holds, whatever that condition is supposed to mean. And so sometimes you draw a number of tokens like that, or you write the number of tokens n, okay? And marking of a Petri Net or a state of the Petri Net is simply a vector where you list the number of tokens in each of the places. Okay? So far so good? There's a lot of information coming to you. I'm trying as filtered down as possible. Now, the next, so far what we described is statics of the Petri Net. Now we will describe the dynamics of the Petri Net, how things change, because it is meant to capture the dynamic behavior of the system. So in this particular net, I have two places and one transition. And I have put a token in that place, the input place of this transition. And by the notion of something called enable, in this particular mark, this is a marking 1, 0, if you will. Marking is simply listing the number of tokens in each place. So in this particular marking, I have 1, 0, right? In that marking, since the condition needed for this transition are satisfied, that transition is said to be enabled. And enable transition may fire. It doesn't have to fire, it may fire. When it fires, it will take away a token from each input place and deposit a token in each output place. In this case, it will take away a token from that place and deposit a token in this place. So marking has changed from 1, 0 to 0, 1. So enabling of transition and firing of transitions, okay? This is the dynamics of the Petri Net. Now we can give, I'll skip this example. Okay, this is a more interesting example where I have 2 transitions and 3 places, and the transition T1 has 2 input places. So there can be multiple input places, there can be multiple output places. Now in order for that transition T1 to be enabled, I need at least 1 token in both input places P1 and P3. So suppose that gosh, what is happening? This didn't work well. Somehow it used to work well. Something went. So suppose there is a token in P3 and P1, then transition T1 is enabled, and it will when it fires, it will take away that token, and deposit a token there. Okay, that's what I want to demonstrate. But somehow this token game went a little bit off. When you move from one set of slides to another set of slides, who knows what PowerPoint does to you? Yesterday I wanted to throw this machine, you know. I don't know whether this machine or the software on that machine is the problem. I think Bill Gates is the problem, right? He made billions and he makes us all suffer. I'm being taped, my God. You know, his wife is a big donor for Duke. So she got her degree from Duke. And this may be a case of a tenured professor being fired, you know, who knows? Now, this notation allows me a lot of things. For example, if I had different sectors failing in my smart grid, so T1 firing may indicate failing of sector 1, and T2 firing may indicate failing of sector 2, and these 2 are happening independently and concurrently. That's perfectly okay, right? It may be that in order for me to lose power, I need to lose 2 different supplies. So both these supplies have to be failed before I lose power. So this is synchronization, right? So, so there are a lot of interesting features. But now let me get to what is called reachability graph. So suppose that I have this Petri net given to me, or I have constructed, and it is taken to model a system with 2 processors or 2 lines or whatever it is you want to call it, okay? So 2 tokens in the up place indicates that both these processors are up and running. Processor is what I normally talk about, not sectors or whatever, okay? Is that okay? So 2 processors are up and running fine. And in that particular marking, which is 2-0, if you will, 2-0, right? What are the enabled transitions? Maybe I should ask you. T-fail is the only enabled transition because the input place of this transition has no tokens, right? Input place of that one has 2 tokens. So when it is enabled, eventually it will fire. And when it fires, it will take away 1 token from there and deposit a token here. And therefore, the new marking that results is 1-1. In this marking, what all transitions are enabled? Both transitions T-fail and T-repair are enabled. So there is a competition between the 2. And there are a number of different ways in which competition is resolved. But if this one fires first, it will take away this token and deposit a token there, returning to the original marking. Or if this one fires first, it will take away that token, depositing 1 here and resulting in this marking. And from this marking, again, you can go this way and so on. So I have 3 different markings that result from the operation or dynamics of this Petri net. And this can be in a shortened form indicated here. First marking was 2-0, and from there you move to marking 1-1 via the firing of transition T-fail, etc., etc. So what I have now is what is called a reachability graph of the Petri net. Okay? Yes, sir.
I mean, this shows that Petri nets are stochastic.
No, not yet, not yet.
Well, you could have, you didn't know. If it fired to 2-0 or 0-2. So in the ordinary Petri net, it will be a sequence of this can fire or that can fire. Yeah. You call it non-stochastic or deterministic instead of?
No, that is left open. That is left open. But stochastic Petri net wise, there are, and we'll come to that, yes.
So short comment on it.
Yes.
It is confusion in the terminology. In books you frequently can read that Petri nets are describe non-deterministic behavior. And it is because of this property that enable transition may fire. And you never know when. So if you have many of them, one of them will finally fire, but it is non-deterministic.
So at the Petri net, all possible sequences will be studied, basically. Right? So far I'm still doing Petri nets. So the first step, one thing you can do with Petri nets is reachability graph. And so the reachability graph is a directed graph whose nodes are the markings in the reachability set with the directed arcs between them indicating the marking to marking transitions, and directed arcs are labeled with the corresponding transition whose firing results in that marking change. Okay? Now, of course, in this particular innocent example, the Petri net size and the reachability graph size is very similar, but in general, reachability graph is much, much, much larger and sometimes infinitely large, corresponding to the Petri net under consideration. And there are many extensions people have done. One is arc multiplicity, and the other is inhibitor arcs. Very quickly, we can go through what that means. So earlier, we were assuming that, for example, when this transition fires, it would deposit one token here. But I can have m tokens being deposited. That's the multiplicity of arc. Similarly, this p here indicates that in order for this transition to be enabled, at least p tokens must be here, not just one. And when it fires, it will take away p tokens. That's the multiplicity of the arc. Okay? And the other notion is that of an inhibitor arc. So inhibitor arc is denoted by the circle at the end of the arc, and the meaning is that for this transition to be enabled, there should be at least one token there and no token here. All right? So in this case, the Petri net token game is happening. Let's see if it really happens correctly. Well, so point is that if there is no token here and a token there, then it is enabled. Okay? And when it fires, it will take away a token from there, but will not do anything to this. So this is simply checking whether there is nobody there. More examples. So this particular case, yeah. So transition TK is enabled now, right? Because there is a token in the regular input place and no token in the inhibitor input place. So when it fires, it will deposit 3 tokens there. It will take away that token. Okay? Something went wrong with this. It was working. I don't know when I transported to this set of slides. Okay, so now stochastic Petri nets. So you understood Petri nets. Any questions on Petri nets? And there is in fact, Denmark is a very, very big site for Petri nets, and Europe in general more so than US. So Petri nets are extended by associating time with firing of transitions, resulting in time Petri nets, and a stochastic Petri net, and of course different people may have different definitions, where the firing time has exponential distributions. And so it's not too difficult to see that the reachability graph of an SPN will become homogeneous continuous time Markov chain, abbreviated CTMC. Okay? So we can quickly go through some examples. So on the left, I have a Petri net on the left top where I have a token in place P1, which means that transition T1 is enabled. And transition T1 here, in my mind, is a failure transition for that component. And it has attached to it an exponential distribution, and the corresponding parameter lambda is the failure rate of that particular component. And when T1 fires, which will be after from the time of enabling until firing. The time is exponentially distributed with parameter lambda, or mean 1 over lambda. When that fires, it will take away a token from P1 and deposit a token in P2, resulting in this marking. And in that marking, transition T2 is enabled, which is the repair transition. Again, exponentially distributed repair time with mean 1 over mu. When that fires, you go back to where you were. So we have a simple two-state situation, which reachability graph is given here, 1, 0, 0, 1. Firing of T1 takes you from this marking to this marking. Firing of T2 takes you from this marking to that marking. And when I replace the name of the transition by the rate of the transition, I have, lo and behold, homogeneous continuous time Markov chain. In this particular case, Petri net is slightly more complex than a Markov chain, but yeah, I can put n tokens over there representing n components. Petri net will be more or less the same, but the Markov chain will be larger, much larger. People are getting the point? And one other construct is necessary in order to go forward, is something called marking dependent firing rate. So when I put a sharp sign next to this arc, it means that the actual firing rate of this transition is going to be lambda multiplied by the number of tokens in this input place. And that is necessary if you look at this simple extension of the earlier model, where I have n components in my system, n processors. In this case, I have taken channels in a wireless system or something like that, because he likes wireless, right? I have put a sharp sign there in front of the failure transition. And then when you see the Markov chain underlying, you will see clearly that when we are in state C, there are C things that can fail. And therefore, the overall failure rate is C multiplied by lambda, or C divided by MTTF. So that notion has to be conveyed through the Petri net, and that is the marking dependent firing rate. So with this minimum thing, you can generate Markov chains and automatically from Petri nets and solve. This is the contribution from Malloy from UCLA, and simultaneously French people, Natkin and Florent. And this is a unique case I have seen. Joint dissertation, and all their papers were joint. They were always together, twins, Florent and Natkin. And then somebody came along and said, hey, this is good, but not really useful. What I really need is something else in addition to all this. And what then that is that in SPN, all transition times were exponentially distributed. Somebody said, but I need sometimes simply to do some logic. So the transitions that take 0 time, these are called immediate transitions, and that was added by the Torino team led by Balbo, Gianfranco Balbo, and they gave the name to this new construct, the new Petri net construct, which allows for 2 types of transitions: 0 time or immediate transitions, and finite time exponentially distributed firing time transitions. And that gave rise to GSPN. And all of a sudden, the popularity increased, the usability increased. How am I doing on time?
I think you have about 15, 20 minutes. 20 minutes.
Okay, good. So now, but the complication arose when that happened. Usability increased, but complication came in. So when you look at the markings, you know what is a marking? Remember? Tell me what is a marking?
It's the numbers of tokens in the different places.
Number of tokens in different places. So, and in a marking, you move out of the marking because of firing of a transition, right? Now, if the transition that moved you out of the marking was an immediate transition, then what does it mean with respect to the marking?
Changes at the same time?
Pardon?
Everything changes at the same time?
Instantaneously, yeah. Right? So the amount of time you spent in that marking is 0.
Right.
Whereas if you moved out of that marking because of the time transition firing, the amount of time you spent there is non-zero. So if you eventually look at the probabilities, then probability of being in the marking with 0 time is 0. And so these markings were called vanishing markings, and they found a very easy way of eliminating those markings without any effect. And when you do that, then you get a continuous time homogeneous Markov chain. If you didn't, what you have is a mixture of discrete time Markov chain and a continuous time Markov chain, which can be treated, if you will, without elimination, but they chose the elimination method. So now it got a little bit more complicated. After generating the reachability graph, you got to get rid of the vanishing markings, and then you get homogeneous continuous time Markov chain, which you solve to get the answers that you wish. Okay? So that's what I'm saying here. And this shows an example of GSPN, where there's a time transition and there are immediate transitions. And the reachability graph is now called extended reachability graph. And there is a systematic method of elimination of vanishing marking to get you a final graph, which then becomes homogeneous continuous time Markov chain, which only has the tangible markings, not non-vanishing markings. So now back to our section failing, right? So I had my student, because I'm not too good at drawing, right, very quickly. So over the weekend he was working with me. He's sitting over there actually he's sitting in New Jersey right now he's a summer intern for Alberto Avrizar. And I made him draw the GSPN for the Markov chain that we had way back when I started for the section of a smart grid failing. So far so good? Okay, so the last useful extension, and beyond that I won't go, is something that I have done with my former students, which we call stochastic reward nets. So it's an extension to GSPN. Now if somebody says generalized, so how do you generalize the generalized? I don't know. Right? So they preempted generalized. There's no more generalization possible. So we call them stochastic reward nets, our extension. And so one thing we allowed is that, you remember that firing rate in a GSPN could be dependent on the number of tokens in one of the places. So we allowed much more extensive marking dependencies. We allowed priorities to transitions. You say some transitions have higher priority than the others. We allowed the definition of reward rates. Remember I briefly mentioned Markov reward models way back? And so reward rates can be assigned at the net level. So you generate not just the Markov chain, but Markov reward model, and which will allow you to get all the outputs you desire. We also allow for, and these are all needed in kinds of things we want to do. Cardinality of the arc can be variable. Up till now it was fixed at some value. And in addition we allowed something called guard functions. So guard functions are actually disabling functions. Under some conditions, which may be global, you may disable a set of transitions beyond what is indicated by the arcs of the transition. And so this is an example of guard function. I can omit that. So so the overall structure then, you have a stochastic reward net you have defined, and our tool or other people's tools will automatically generate the underlying reachability graph, extended reachability graph, eliminate the vanishing markings, and what results is actually Markov reward model, not just Markov model. And then you solve that Markov reward model again automatically, either for steady state behavior, transient behavior, cumulative transient behavior, all kinds of behaviors, and then finally get the measure of interest. So user is shielded from all the gory details and error prone tasks. So far so good? Now this is something that I haven't checked out with my colleagues at Siemens. As I told you, my student under my direction from here came up with the SRN model for that single section failing, and this allows us to generalize then in my mind without checking with my colleagues. So one section failing, another section failing, third section failing, so 3 sections are failing at once, and I'm checking whether active power is enough, reactive power is enough. And of course underlying Markov chain will be much larger, and I have not much of a hope of doing it by hand, but if my colleagues agree that my Petri nets are fine, then we can do this for many different sections failing. So simultaneous failures or cascading failures can be done, and so on. As I said, this is just for you. Nobody else has seen it other than me and my student, okay? And this will be checked out with the Siemens guys, including Sindhu, who is a power person, and then we will finalize. So far so good? Okay, so now to give you some completed examples, very, very briefly. So this, for a while I've been dealing with infrastructure as a service cloud, its performance models, availability models, power models, and so on. So this is a stochastic reward net model of infrastructure as a service cloud availability model. And this work was of interest to IBM. This was done jointly with IBM Research. And it turns out that in IBM Research Cloud, the physical machines, or PMs, were divided into 3 pools: hot servers, warm servers, and cold servers. So this one indicates the three places here: the number of hot servers initially, number of warm servers initially, number of cold servers initially, and then servers can fail, can get repaired, they migrate from one pool to another. All that is captured here. And here are the guard functions that are necessary to get everything going. So it's an SRN, stochastic reward nets. And what is interesting is that when you run that stochastic reward nets, depending on the number of physical machines in the pool, the number of Markov chain states can get very large, and the number of non-zero entries in the matrix of the Markov chain get very large. And still you can, in a reasonable time, solve such models. There is no hope of doing construction by hand of such models, right? And there are many other examples I can give you. I just chose one like that, okay, for performance, for reliability, availability, survivability, performability, all under many different types of systems. Now, I promised to you that I will also briefly tell you about the extensions beyond. So one set of extensions is to non-Markovian Petri nets. And this work was done in 1993 by a student of mine and a colleague from operations research at University of North Carolina at Chapel Hill. We call them Markov regenerative stochastic Petri nets, which allows, in a limited sense, non-exponential distributions. And there are a number of other papers along those lines. And the other extension, which I'm really hoping that can be used in the context of smart grid to capture voltages, phase angles, and the failures, repairs, and such things, a demand response, and all together in one place, is possible by means of fluid stochastic Petri nets, where the number of tokens in a place is allowed to be a real number, not just an integer. And that's why we call them fluid stochastic Petri nets, FSPN. This work was also originally done with my friend Kulkarni at University of North Carolina at Chapel Hill, where we allow both discrete and continuous places in which discrete tokens can be held, and places in which continuous fluid tokens can be held. And so pictorially, you can see the pipes, and so the continuous places are indicated as double circles, and tokens are indicated there by fluid levels. And the input arcs here will be pipes, and output arcs will also be pipes from the fluid places. So you have both jointly continuous and discrete places, which is a very, very powerful medium to express what are called cyber physical systems, if you will. And so all this stuff is put together in our tool called SPNP, Stochastic Petri Net Package, which indicates all these paths possible. So suppose that the net that you have is a Markovian net, in which case extended reachability graph will be generated, Markov reward model will be produced, and what we call analytic numeric methods of solution will be adopted, either for steady state or transient, and even the methods are given here, some of it overdeveloped and somebody else. If the net is either non-Markovian or FSPN, although analytic numeric solution is possible, what is implemented in SPNP is discrete event simulation, which may be also for steady state behavior or transient behavior. And there are all kinds of interesting simulation methods implemented there, like importance sampling, restart, splitting, and so on, for fast simulation. And even a Markovian net, you may want to simulate if the underlying reachability graph becomes so large as to be not be able to store in the machine. So that ends my talk, I'm sure I put, no, actually I don't see anybody sleeping. I'm surprised. You know, when we, maybe 15, 20 years ago, we started closed circuit TV course sharing between the 3 campuses of North Carolina, UNC Chapel Hill, North Carolina State University, and Duke University. And I think I was sitting in somebody else's course. I'm protecting myself here. What they do is each of suppose this campus is transmitting. The other campuses, there'll be a monitor and students or people sitting there. But in one particular case, there was only one student, so monitor decided to leave. And the student started to snore. And everybody in the other campuses can hear him snore, you know, see him and hear him snore. So it is possible people go to sleep. And it's easier though, if you're in a different location and somebody is not talking as loud as I am, right? Actually, one time, one student wrote that one difficulty with this professor is very hard to sleep in his class. Sorry, I talked too loud. Anyway, any questions, comments, tomatoes? No eggs. Yes?
I know for discrete Petri nets, there is a notion of equivalence called bisimulation or something like that. Is there something for stochastic Petri nets?
Actually, somebody once wrote a paper along those lines, but I'm not very familiar with that. I think somebody from Erlangen, if I'm not mistaken.
Okay.
Yeah. Anything else? Sir, are you okay now?
Yeah, I'm still a little bit confused with the
Non-determinism versus stochastics.
Yeah. Mismatch in terminology, as I said.
Yeah, it's problem. Yeah. Whether you put time or not. Similarly, in the stochastic process algebras, there were process algebras.
And you play also with time and probability in a nice way that confuses me a little bit when you go back and forth between timing, which is...
Okay, I can elaborate on that.
I mean, timing for you is like the... if you have a high probability, you have a high rate, and the timing becomes the relationship between the rates of different processes to me.
Okay, so
it's relative time to me.
Okay, so which way shall I?
The rates of processes.
I see what I see what you're getting at, and let me see if I can elaborate.
Switch between them very rapidly is confusing.
I can see. Okay, so this particular case is interesting, right? So suppose there is a token here. Then the token, there's a competition between these two guys to grab that token, right? Now these two transitions are both immediate transitions. They will take 0 time to fire. So if I tell you I have two guys who run infinitely fast, can the competition ever be resolved? No, right? So the way in which this is done is you put a probability. So with probability u, this will fire. With probability 1 minus u, this will fire. So here, so therefore that is reflected here. You get out of this marking, which is a vanishing marking. With probability u, you go to this marking, which means token will be deposited here. And with probability 1 minus u, token will be deposited here. So there is a probability here on the edges of the graph. Now if I give you a graph in which all edges are probabilities, that's a discrete time Markov chain. Whereas if I give you a graph where all edges have rates, that's a continuous time Markov chain. Now it turns out that most people who learn Markov chains just learn discrete time Markov chains. They don't learn continuous time Markov chains. In fact, many people actually will twist the continuous time Markov chains to look like the discrete by putting a delta t, and I never liked that mess, okay? But some books, well-known books, do that because they have never learned continuous time Markov chain. Continuous time Markov chain is a beautiful, beautiful construct. So suppose that, do I have an example? I don't have an example. Yeah, I can write somewhere, right?
Yeah, you can just select.
Where is this?
There are pins here.
So that's one type of competition you saw. The other type of competition.
Or you could use this one or this one.
Yeah. Oh, I can write here. So if there is a token here, no? What happens?
This one. That one doesn't come up.
Okay. Okay. If there is a token here, and these two transitions, which are time transition, are competing, that's what you are referring to, right? Okay. What happens here? In my setup, both these times are random. So this is exponentially distributed. Let's say call it that time x and this time y. And what does the distribution mean? That sometimes this may win, sometimes that may win. How is the competition resolved? Well, you can actually compute this probability x is greater. So suppose this is lambda and this is mu. Okay, the rate is lambda and mu. Then you can find that the probability x greater than y will be lambda divided by lambda plus mu if you want to find the probability. Okay? So from distributions you can get to probabilities like that. This is all covered very well in my book. Unfortunately, people don't know about it for some reason. Probability and statistics with reliability, queuing, and computer science applications. So this is chapter 5, very, very clearly indicated. Okay? And chapter 7 is discrete time Markov chains. Chapter 8 is continuous time Markov chains. And as I told you, many books, well-known books on fault-tolerant computing, do not tell you about continuous time Markov chains. And they do this funny thing. They will do a very funny thing. Instead of this one, you will see, I don't want to name the books, but they will do this, you know. And then they will have to do this. This is bordering on wrong, if not. But many, I can name the books, okay? They're considered very well-known books. One from Virginia, for example. Right? And I have tried to tell him that, you know, when I was working with him, but he just wouldn't listen. Okay? So continuous time Markov chains have rates on the transitions, and discrete time Markov chains have probability on transitions. What I showed you in this example is both rates and probabilities. That's why you got to get rid of the probabilities and get only rates.
I understood it after some time.
Okay?
It was another perspective or another view, another type of abstraction.
Yeah, the people's terminology slightly.
You have to become used to.
Pardon?
You have to become used to the abstraction or to the perspective.
Yeah.
Okay.
Any other questions, comments? No? Can I tell my wife I did a good job?
Okay.
Okay.